Yeah, as we have seen the multinomial distribution, now it's pretty easy to understand chi-square distribution. So we will see. But before we understand the chi-square distribution and how to use it in data science and what all we can do with the chi-square distribution, such as goodness of fit and then all those things, we will see the history of this, how this has come up. First thing, how this chi-square distribution have come. That's important, na? If you understand that, then you can easily take leverage of chi-square distribution better. So the chi-square distribution was developed by the English statistician Carl Pearson in the late 19th century. So Pearson was interested in developing statistical methods to study the relationship between two categorical variables. So he realized that in order to compare the observed frequency of a categorical variable to the expected frequency, he needed a new distribution that could handle the squared differences between the observed and the expected frequency. Now, my question is, does everybody know what is the expected frequency? You know, observed frequency. We know what is observed frequency. So let me put it here. This one is chi-square distribution. Okay. So we know observed frequency. For example, if you take observed value after doing the experiments, whatever value that you get is a observed value. Whereas the expected frequency, that's what the predicted or forecasted. So that's why let's understand what is expected frequency. Observed frequency is pretty clear. So expected frequencies are the frequencies different outcomes that we would expect to observe under a certain hypothesis or assumption. So if we take one example that uh, for the Pearson for that to explain that Pearson's concept, how he came up, I just want to take up one example. So that example is a variable with three categories: A, B, and C categories. In this example, let's see what is expected frequency. Okay, so now uh, to calculate the expected frequencies, we need to specify a probability distribution for the categorical variable. So this is our categorical variable, which consists of three categories. For example, if we assume that the variable follows, let's take this variable follows multi this variable follows multinomial distribution. If it follows multinomial distribution, so then obviously each one will have their respective probabilities. So first one is PA, probability of A, and probability of B, then probability of C. So these are the probabilities of respective categories in A, B, C of categorical variable. So now how much it will have? The total size, let's check. If we go for the sample size of n, then the expected frequency of this outcome, because see, we have not done any experiment, so we know these are the three categories under this variable, and we know that this is following the multinomial distribution. Then obviously if it follows the multinomial distribution, then we can get the probability of each category from the multinomial distribution. So we have taken that multinomial distribution probability, and then now we are calculating the expected frequencies. Expected frequency for category A is n times PA, and for other things also applies same. Yeah. So for other category B and for other category it's C, and this is how it works. Okay. So this is what we call it as an expected frequency. So expected frequency is the one that frequency has been calculated from the probability which was plotted through any distribution, probably any distribution. That's what is called expected frequency. Expected frequency is the value that you have computed from the probability of the distribution of that specific variable. Okay. So now the reason Pearson was expecting certain frequencies is because he wanted to test whether the observed frequencies were consistent with a particular hypothesis or assumption. So by comparing the observed frequencies to the expected frequencies, he could determine whether the data provided evidence for or against my hypothesis. So that's what the expected frequency. So now let's continue with the how why the chi-square has come into the statistics. So that's what then. So Pearson developed the chi-square. So Pearson was interested in developing statistical methods to study the relationship between two categorical variables. So he realized that in order to compare observed frequencies and expect observed frequencies of a categorical variable to the expected frequencies, he needed a new distribution that could handle the squared differences between the observed and expected frequencies. Then Pearson developed the chi-square distribution by taking some of the squares of normally distributed variables, specifically if we take a k independent and standard normally distributed variables with mean 0 and variance, then the sum of their squares follows a chi-square distribution with k degrees of freedom. So the chi-square distribution is now widely used in statistical hypothesis testing, particularly for goodness of fit tests, tests of independence, and it's an important tool for data scientists to understand and use in order to make statistical inferences and draw conclusions from categorical data. So suppose then the Pearson, suppose we have a categorical variable with possible outcomes a, b and c. So we observe the variable for a sample of n individuals and count the number of occurrences each outcome. Let's say we expect the probabilities of outcome capital A, capital B, capital C to be PA, PB, PC respectively, that you can see on the screen here. So now Pearson wanted to test whether the observed frequencies of outcome A, B and C were significantly different from the expected frequencies. To do this, he first calculated the squared difference between the observed frequency of A minus expected frequency of A whole square divided by expected frequency of A. So to do this, first he first calculated the squared difference between the observed and expected frequency for each outcome. So he then added up all these square differences to obtain a test statistics, which he called the chi-square statistic. So chi-square, an observed frequency of a, the first component plus second component plus third component will give you the chi-square test statistic. So Pearson showed that the chi-square statistic follows a chi-square distribution with 2 degrees of freedom. So he used this distribution to derive critical values for his hypothetical test and to calculate p-values of the test. So this example demonstrates how Pearson used the squared differences between observed and expected frequencies to develop the chi-square distribution as a tool for statistical hypothesis testing.